Hey guys, so we are very, very, very close to arriving at the Schrodinger equation. Okay, so right now I've got a few, or six actually, special wave functions up here right now. And what's special about them is something I will explain very shortly. But this is going to be a crucial, crucial, crucial step in getting to the Schrodinger equation and indeed getting to all the rest of quantum mechanics. And this is the first time, well, actually, not the first time, because we did a few videos ago when we were talking about K-space. But we are going to really invoke the de Broglie relations and the wave-particle duality. So, what I have here in green, in regular, these are wave functions of x, and what the and so what this is the wave function with a definite value of position, right? Delta of x minus x naught with the definite position of x naught. We've talked about that before, why the delta function works, and that mathematically it makes things really nice. Phi sub p naught, right? The wave function with the definite momentum is e to the I k naught x, and in fact, there really is a 1 over root 2 pi here, right? But for the purposes of this video, we don't actually need to have that there, and it's just going to make things more messy. And you can hopefully see by the end of the video that if you put the 1 over root 2 pi there, everything would be exactly the same. It would just be messier. So I'm not going to have that there. And the reason this is the wave function with a definite momentum is because p naught will equal h bar k naught. Now we go to energy. And for right now, we'll call this the wave function with a definite energy. Pretty soon, we will find that there is actually way more to that. And in fact, finding the wave functions with a definite energy will be our job throughout the entire, throughout most of section 4 and throughout most of quantum mechanics in general. It's a very, very, very big job. So it's not this simple, but this is one way to get there, right? Which is at least the time part, right? And these are wave functions of time, and I'll tell you why this one doesn't really make sense, but it's important to have up here. But the time part of the wave function doesn't make sense to just have a wave function as a function of time, because that would imply that there's a probability of finding the particle at some time, or right? But a wave function can evolve in time, so it can be a function of time, but it can't really be a function of only time, right? So this is obviously an incomplete picture, but it's important. The general form for a wave, if you remember a video about mechanical waves, would be sine or cosine of kx minus omega t, right? Or in terms of exponentials, which are the more general way of writing waves, this is e to the I kx minus omega t, or also e to the I kx minus I omega t, right? And so the wave function with a definite value of energy, right, because E naught will equal h bar omega naught, that is part of the wave-particle duality, the de Broglie relation, this, right, and there again should be a 1 over root 2 pi here, but we don't need it there. So yeah, there's a 1 over root 2 pi anytime we have this exponential in general. This one, that one, they should all have that 1 over root 2 pi factor. But it will just make things messier. So hopefully this is convincing why, just given the wave-particle duality, this should be the wave function with a definite value of energy, because it has a definite value of omega in the angular frequency. And a wave function with a definite value of time, which makes absolutely no sense, but we can theoretically write it down. And in fact, if you put this with a position, this would actually this would really be, I mean, the interpretation of this delta function is literally that you can only find the particle at one and only one time, which is really just as crazy as it sounds. But if we were to write a wave function like that, theoretically, it would look like a delta function, delta of t minus t naught. Not a physical wave function. It won't be important, but it will be important when we're looking for the time operator, which will be important for some other reasons. Lastly, if we work in momentum space or k-space, we know that we talked about this before. Phi tilde sub x naught of k, right, is 1 over root 2 pi times e to the minus ik x naught with a definite position of x naught. Phi tilde sub k naught of k is delta of k minus k naught, right, where p naught equals h bar k naught. Okay, so now we know that these are the eigenstates, right? This is the eigenstate of x hat. This is the eigenstate of p hat. This is the eigenstate of e hat, right? Because this is the eigenstate of t hat. This is the eigenstate of x hat in the momentum basis. This is the eigenstate of p hat in the momentum basis, right? With an eigenvalue, this eigenvalue would be x naught, the eigenvalue would be p naught, or h bar k naught, the eigenvalue here would be e naught, or h bar omega naught, eigenvalue here would be t naught, here would be x naught, here would be h bar k naught, right? So let's figure out what these operators are. So I think really what I'm going to do is I'll tell you what the operator is, and then you'll just, we'll just prove that it works, right? So I'm going to say here that x hat equals, is really defined by just multiplying by the variable x. And the reason this works is if we take x hat times phi sub x naught, right, which is, that would be x times delta of x minus x naught, right? But this delta function, right, or this x, this thing is going to be 0 whenever x does not equal x naught. So this is the trick that we've used a lot of times where we can just turn this is x naught delta of x minus x naught, and this is equal to x naught phi sub x naught, right? So multiplying just by the variable x, multiplying the Dirac delta function by that variable x will actually give you the x naught, the definite position x naught, times that Dirac delta function, right? That's the Dirac delta trick that we've been working. And this is exactly what we want, because if you remember q hat, right, if q naught is the value of the observable, q hat psi, or phi sub q naught, equals q naught phi sub q naught, right? This is what we're trying to show this entire time. So I'll leave that up there at least for the next few. So now I'm going to write down that p hat is defined as I h bar, and then I'm going to use, instead of a regular derivative, I'm going to use a partial derivative, d by dx. The reason is we're going to start working with the wave functions of both position and of time. And so because of that, we want to be able to, specify this as a partial derivative, right? But note, and you can prove this too, just using, calculus and fairly common sense, if you really understand, the Hermitian conjugate of the partial derivative, similarly, just like the derivative, is negative of itself. And now, notice, number one, since x is real, right, position has got to be real, this is a Hermitian operator because that was number 1 in our last video. This was number 5 in our last video. We've got some real constant, h bar, times I, times a derivative. This is a Hermitian operator, right? We've got to make sure these are Hermitian. And you can show, and actually I'll show right now, p hat times phi sub p naught of x, right, is equal to, this is I h bar partial x e, and remember that you can see you'll be able to pull that factor of 1 over root 2 pi out, e to the I k naught x, right? If we take the derivative, this is I h bar times I k. Oh, sorry, I did make a mistake. This is negative I h bar. My bad. So that's negative I h bar. So this would be negative I h bar, right? Which is still the same thing because then our constant would just be negative h bar. So this is still Hermitian. So negative I h bar times I k e to the I k naught x, right? Well, negative I times I is 1, right? So this is h bar k naught, this is a k naught, e to the I k naught x, which is p naught, right? Phi sub p naught of x, right? So this shows that given this state, right, and you can do it with the 1 over root 2 pi, p hat will be negative I h bar d by dx. Okay, so now I'm going to erase this, and the rest of these, showing them, is the exact same. So I'm going to skip the proofs, and I'm just going to write down what these operators are. We have e hat will be positive I h bar. So you can see because these signs are different. Positive I h bar d by dt partial, right? T hat, using that Dirac delta trick, will be just multiplying by the variable t. Now, x hat, actually I think I'll write x tilde hat, right? In the, thought that would look better, but it doesn't. So it really doesn't make a difference, so I'm going to write it the way I'm more used to. X hat tilde, right? X hat in the momentum basis is not going to be just multiplying by the variable x, because the variable x doesn't exist in the momentum basis. The variable is k, right? And so in using this trick, you can show that this is I h bar, positive I h bar, d by dk, right? Wait, it is not that. Sorry. No, it is not that. There's no h bar. It is, sorry, I think I wrote that wrong in my notes. It is I d by dk. Okay? It's a partial derivative. Okay? And finally, p hat, and I don't know why I wrote k naught here. I should have written p naught. P hat in the k basis is just equal to multiplying by h bar k, right? Because k is the variable, right? And you could do this with a variable p. It's usually more standard to do this with a variable k, so that's what I did. So these are all of the operators, at least for right now, that we are going to be dealing with. And I will see you in the next video.